It's from Schrödinger's equation that scientists get the concept of atomic orbitals, which are specific regions where electrons are likely to be found. Schrödinger's equation provided an electron density distribution, which is a probabilistic view of where electrons can be. When you look at the density distribution, a three-dimensional shape is clear, and that shape is the atomic orbital, which also has energy associated with it. This is similar to Bohr's model, in which he states that there is an energy associated with each orbit or level. However, Bohr introduced just one principal quantum number n to describe these levels. The revised quantum mechanic model uses four quantum numbers Qn to describe the atomic orbitals. They are n, the principal quantum number, L, the angular momentum quantum number, m sub L, the magnetic quantum number, and m sub S, the spin magnetic quantum number. Let's go into a quick overview of the different quantum numbers before going further in depth. Like Bohr's model, the principal quantum number n has whole number values of 1, 2, 3, etc. As n increases, the electrons have higher energy, the orbital increases in size, and the electrons are spread farther out from the nucleus. The angular momentum quantum number L describes the motion of electrons around the nucleus and defines the shape of the orbital. L has numerical integer values of 0 to n-1 and is generally defined by the letters S, P, D, and F for the numbers 0, 1, 2, and 3. For example, with n equals 2, L is 1p and 0s. The magnetic quantum number m sub L determines how the electron's orbital is tilted or oriented in space. Think of it as the orbital is rotating in the zy axis. It can have the integer values of negative L to 0 to positive L, so when L equals 0, m sub L equals 0. When L equals 1, m sub L equals negative 1, 0, positive 1. And when L equals 2, m sub L equals negative 2, negative 1, 0, positive 1, positive 2, etc. Remember, L equals the integer values of 0 to n-1. Lastly, the spin magnetic quantum number m sub S relates to the electron's inherent property of spin and denotes the direction of the magnetic dipole that is produced by a spinning electric charge. The values for m sub S are negative 1/2 and positive 1/2. The principal quantum number n represents the electron's energy level and can be any positive integer, indicating theoretically infinite possible orbitals for an electron. However, an electron resides in only one specific orbital at any time, with the rest remaining unoccupied. Groups of orbitals sharing the same n value form what is known as an electron shell. So for n equals 2, electrons are located in a second shell. These shells are further divided into subshells that share the same n and L quantum numbers. There are the same number of subshells as n. For instance, at n equals 2, there are 2 subshells. However, these subshells are differentiated into orbitals by the angular momentum quantum number L. These L orbitals have the numerical value of the integers from 0 to n-1 and are generally defined by the letters S, P, D, and F for the numbers 0, 1, 2, and 3. Thus, for n equals 2, we have L equals 0, the s orbital, and L equals 1, the p orbital, leading to the designation of the subshell's orbitals as 2s and 2p respectively. Each L orbital contains suborbitals, its orbitals all the way down, determined by the magnetic quantum number m sub L, which is how the orbital is tilted or oriented in space. These m sub L orbitals range from negative L to 0 to positive L, so an s subshell L equals 0 has one suborbital 0. A p subshell L equals 1 has 3 suborbitals, negative 1, 0, positive 1, and a d subshell L equals 2 contains 5 suborbitals, negative 2, negative 1, 0, positive 1, positive 2. To get a clearer picture, I've constructed a table consisting of the electron's energy shells, subshells, orbitals, suborbitals, starting first with n, of which 1 through 4 are in the first column. The next column corresponds to the subshell that shares the same n and L quantum numbers. There are the same number of subshells as n and includes integers ranging from 0 to n-1. As you can see, with each increasing number of n, the subshell values of L also increase. The subshells are differentiated into orbitals, the third column, by the angular momentum quantum number L. These L orbitals are named by the numerical n quantum number, followed by the letter designations from their subshell that are S, P, D, and F for the numbers 0, 1, 2, and 3. Thus, for n equals 2, we have 2 in the orbital's name, and S for L equals 0, and P for L equals 1, leading to the designation of the subshell's orbitals as 2s and 2p respectively. Next are the suborbitals determined by the magnetic quantum number m sub L that can have the integer values of negative L, 0 to L. For example, with n equals 3, we have L equals 0, and L equals 1, and L equals 2. So the suborbitals consist of 0, -1, 0, 1, and -2, -1, 0, 1, and 2. The next two columns consist of tallying up the suborbitals in the subshells and the total number of orbitals for each n level, showing that the total number of orbitals equals n squared. Remember that the electron density distribution produces three-dimensional shapes known as orbitals, which represent the probabilities of locating an electron. Now that we've delineated the numbers behind the electron shells, subshells, orbitals, and suborbitals, for electrons, let's get into their shapes. Every atom has one s orbital, since it is the orbital that corresponds to L equals 0, and m sub L is also 0. Looking closely at this s orbital, we can see that it is spherically shaped, which is a good way to remember it. But does the shape of the s orbital change as n increases? While the basic spherical shape remains the same, as the principal quantum number n increases, the orbital's energy and size expand. Consequently, the electron density becomes more dispersed, enlarging the sphere and increasing the likelihood of finding the electron farther from the nucleus. When n is greater than or equal to 2, p orbitals are present, which have a much different electron density distribution than the s orbital. The density is concentrated in two lobes on either side of the atomic nucleus, which resembles a dumbbell shape. The space between the lobes around the nucleus is where the probability of finding an electron is virtually 0. We call this a node or a nodal plane. There are three orbitals in the p subshells corresponding to the -1, 0, and +1 potential values of m sub L. They are labeled as p sub x, p sub y, and p sub z, indicating their orientation along the x, y, and z axes respectively. Similar to s orbitals, the energy and size of them increase with n as they go from 2p to 3p and so on. Next are the d orbitals, present when n is greater than or equal to 3. There are 5 d orbitals corresponding to the -2, -1, 0, +1, +2 potential values of m sub L. 4 of these d orbitals have a cloverleaf pattern and are labeled as d sub xy, d sub xz, d sub yz, and d sub x squared minus y squared, corresponding to the planes in which they lie. The last, d sub z squared, has a unique dumbbell shape with a donut ring around the center. Even though it might look different, it still has the same energy as the other d orbitals. The last orbitals are the f orbitals when n is greater than or equal to 4. There are 7 f orbitals corresponding to the -3, -2, -1, 0, +1, +2, and +3 potential values of m sub L, and have an extremely complex shape that we won't get into. While we won't get into their representative shapes, they are crucial to be aware of for the electronic structures and configurations of elements that we're going to get into. The last quantum number, spin magnetic m sub s, was discovered through physicists' detailed examination of atomic line spectra. What at first appeared to be single spectral lines were actually closely paired lines, indicating twice as many energy levels as expected. This observation was pivotal in uncovering the concept of electron spin and the introduction of the fourth quantum number, the spin magnetic quantum number m sub s. This phenomenon arises because a spinning electron is like a charged sphere and generates a magnetic field dipole with distinguishable north and south poles akin to a bar magnet. The orientation of this magnetic field is quantized, existing in two opposite directions, represented by spin values of +1/2 spin up and -1/2 spin down. These orientations correspond to the two possible values of m sub s, fundamentally influencing how electrons are arranged among an atom's orbitals. In 1925, Wolfgang Pauli's discovery of the Pauli exclusion principle was the final key to physicists being able to accurately represent electrons in their respective orbitals in an electron shell. This principle states that no two fermions, particles with half-integer spin, such as electrons, protons, and neutrons, can occupy the same quantum state within a quantum system simultaneously. This means that no two electrons in an atom can have the same set of all 4 quantum numbers. If 2 electrons are in the same orbital, thus sharing the same n, L, m sub L, they must have opposite spins, m sub s, to satisfy the principle. Simplified, this means that an atomic orbital can hold a maximum of 2 electrons, and they must have opposite spins. A diagram for this for 2 electrons in the 1s orbital would look like this. The half arrow represents 1 electron, and you can see that one is pointing up while the other is pointing down. We'll get into the full representations and arrangements of the many electron orbitals in the upcoming unit, electron arrangements. Thank you for watching, and I hope these explanations help. If you have any further questions, feel free to ask. And if you found value in this video, please like it and subscribe and let people know about the channel, because it really does help spread the knowledge. Based on what you learned, think about the following question. What quantum numbers are used in the quantum mechanical model to describe atomic orbitals? How did the discovery of the closely paired spectral lines lead to the understanding of electron spin and the introduction of the spin magnetic quantum number? Pause now to work out the answers. Principal quantum number n, angular momentum quantum number L, magnetic quantum number m sub L, and spin magnetic quantum number m sub S. They suggested that there was an additional form of quantized energy that physicists were missing, which explained the additional splitting.